Yeah, I would also, of course, like to thank the organizers. It's nice to be back at ICTS. So I think this is the only talk on filtering theory. From at least the titles, that's what I gathered. So I will spend some time in explaining the problem I'm interested in the first place, and then show some of the results. So let's see how much time it takes. Okay, so I will first talk about filtering theory in general, and then Kalman filtering in particular. So the main problem we are interested in is the following. Suppose you have a Markov chain, and I will only talk about discrete time Markov chains. With x naught is unknown, and hence we assume that we have a probability density for the initial condition. The filtering theory problem essentially is, suppose you are given observations about the system over a certain time period. You want to understand, estimate the state of the system, state of the Markov chain at various times. If you consider estimating the state at time during which the observations are given, it's called a smoothing problem. Estimating the state at time tn at the end of the observation period is filtering problem, and estimating the state at times beyond the observation time is called a prediction problem. So in most applications, which is what I'm interested in earth sciences, since the data is collected continuously in time, we would essentially be interested in filtering problem. You have data up to a certain time, and you simply estimate the state at that time, and you keep doing it, if possible, iteratively. And also the other motivation is the prediction can be done using basically the state estimation at a given time. So in the probabilistic language now, this can be transformed into a problem of studying distribution functions, probability distribution function, which are conditioned on the observations. So in all the filtering theory literature, the main assumption is that the observation at a given time is dependent only on the state at that time, plus some noise possible. And so this observational noise will come back to it later. I will take it to be IID, yeah. Independence is crucial. But identically distributed is just convenience, that's not necessary. Okay, so yeah, independence in time will be crucial. Otherwise you can't really form a filtering theory problem, you have to make a smoothing problem. Okay, yeah, so we'll also assume the independence between the prior distribution or the distribution at time t equal to 0 and the distribution of the noise. And so the main object of interest will be the posterior distribution, the distribution of the state conditioned on the observations. And essentially we will only be interested in this filtering problem where it's conditioned on the observations up to that time period. Okay, so the filtering density satisfies a recursive relation in general in nonlinear filtering problems in the discrete time setup I've done. And it can be split up nicely into two steps. One is prediction, the other is update. The prediction is simply follows from the Markov property that if you have, okay, so if you basically call, if you have a distribution up to time t, given observations up to time t, which is this thing, it can be used to predict the distribution at time t plus 1 given the observations up to time t. So that's a prediction using the Markov transition kernel, and that can be updated by using the observational density. This comes from Bayes' theorem, and that takes us from the distribution up to time t plus 1 given observations at up to time t to the distribution at time t plus 1 given the observations now up to time t plus 1. So you go from time t to time t plus 1 using this two-step process. And that can be combined to write a recursive relation in this form, but it's useful to think of it in these two-step process. And it only involves the Markov transition kernel and observational noise. Okay, so this will be the main object of interest and how the recursive relation can help us understand the properties of this. Okay, in particular, if the model is linear and if the initial distribution is Gaussian, essentially everything inside, and observational model is also linear, then all of the distribution that I just described are all purely Gaussian, and they can be represented in terms of mean and covariance of these distributions. And again, there is a two-step process, a update step for the mean and the covariance, and a prediction step for the mean and the covariance as well. So these simply follow from properties of Gaussian distributions, and there is a certain matrix that comes up that's known as Kalman gain matrix, and this is essentially what Kalman proposed in early 60s and so on. One of the key points for our work here would be to note that the covariance map of the update, I mean the update of the covariance, neither the prediction of the covariance depends on the state itself. The covariance, so to say, evolves by itself, and the state is dependent on the covariance, but not the other way around. And so this is useful to study the properties of the covariance matrices, which has been known in Kalman filtering literature for quite some time. So what we will be, okay, I just said this. So essentially, we have a sequence of update and forecast steps, update and predict steps, and the main question we will be interested in is what happens to this asymptotically in time. Does it converge to something, and if it does, then what are the properties of this converged sequence? Okay, so for the case of, okay, so I should say that essentially, if you have a stochastic model, a lot of the results were known earlier in terms of what the convergence properties are and so on. What we will be basically dealing with is the case of a deterministic model, where in the Markov chain that I talked about earlier can be thought of as a deterministic dynamical system rather than a stochastic. And so that's the main focus here. And in that case, there is, as far as I know, there is nothing known, and this is the first results that we have managed to do. Okay. So what So essentially the main result is that if a certain condition is satisfied, which is called observability condition, yeah, I'll come back to it if I have some time, then the limit simply can be that there is actually a limiting sequence of these covariance matrices for autonomous systems, and that limit can simply be identified by writing down, by essentially take away all the t's in these equations, and that identifies a limit, and that limit is given here. What we are also interested in is that the properties of this limiting matrices are related to the dynamical properties of the system itself. In particular, the null spaces. So in particular, these limiting matrices are not full rank, and the null spaces can be identified with the Lyapunov, with the span of backward Lyapunov vectors, stable and neutral backward Lyapunov vectors. That is essentially these distributions simply collapse onto the unstable subspace, and they don't have a support in the stable neutral directions at all. And this is useful in practice because if this essentially gives us a way to reduce the dimension of the system that you want to effectively consider, because the stable neutral direction in some sense do not matter. We really just focus on the unstable directions, and that's one usefulness of this type of result. Okay, okay, so in particular, the rate at which these eigenvalues decay. So sorry, I said that the null spaces are identified with stable neutral directions. So the other eigenvalues, the eigenvalues corresponding to the unstable directions, the eigenvalues corresponding to these stable and neutral directions will decay, and the decay rates are in fact related to Lyapunov exponents. In particular, they're twice the Lyapunov exponents, and that's what is shown here. But the rank deficiency also actually applies to non-autonomous systems, but of course in non-autonomous cases there is no limiting sequence per se, because these systems, because the non-autonomous dynamics itself depends on time, so there is no limiting sequence, limiting value of this of these matrices. but the rank deficiency is still valid, and now essentially it's valid in this complicated way that the stable, that the projection of these matrices onto the space spanned by stable backward Lyapunov vectors is small, or it goes to 0 in some. And that's what this says, that the projection on the stable Lyapunov vectors is going to 0. So essentially, in some sense, the rank is again equal to or approaches the number of unstable Lyapunov exponents, and the other ones go to 0. But since for a non-autonomous systems, the unstable Lyapunov vectors keep changing directions, there is no collapse to some constant matrix, but there is additional result which I'm not presenting about, in some sense, universality of this sequence independent of the observations or the starting point, but that is still work in progress, so I'm not really. And again, the decay rates are related to Lyapunov exponents, but in this case, of course, it's not so clean. You can't really fit it, you can't really fit a straight line to these kind of objects very well. If you can average over multiple realizations, then you can do it, but it's not so clean as in the case of autonomous systems. Okay, so I will skip the motivation for this since I only have a couple of minutes, and I will simply go on what is the nonlinear extension, which is really the main problem of interest, because in earth sciences for sure, all the models that we consider are nonlinear, but right now there are no good numerical or analytical indications of what exactly is the extension of this kind of result in nonlinear systems, and in particular chaotic systems, which have low dimensional structures which are non-trivial, like the chaotic attractors. The nonlinear extension will most likely involve something like the SRB measure and something that is that involves the SRB measures for these chaotic systems. But we have some very crude numerical indications, nothing really convincing yet. And if you have any ideas about talking about SRB measures and so on, I'll be glad to talk. Thank you.
Are there questions?
Kind of experimental or physical situations you can use this kind of are there any you have some kind of a process and you predict.
Yeah, so I mean, so the nonlinear filtering is routinely used in earth sciences in order to make weather. For example, weather prediction always uses they can't really use full nonlinear, I mean, okay. So in principle, these are actually usable in weather prediction kind of problems. In practice, of course, these systems are extremely high dimensional, so severely approximated versions of it in terms of either Kalman filtering, which is linear filtering really, or some other variation methods are used. But that's a context in which I'm really interested in as well, and that's where it is used.
So when you say nonlinear extension, you're saying that instead of taking a stochastic dynamics, you take a nonlinear.
Yeah, I mean, I would basically like still stochastic. Observations are still.
Yeah, observations are stochastic, but the dynamics is.
But dynamics is deterministic but nonlinear, and in particular chaotic.
This model, you don't change the model based on the decision. Model is given. So then if the model is given, then if I make an observation now, I should be just able to predict what happens next, right?
Yes.
So what is the problem?
Observations are not complete. They are partial observations and they're noisy.
Okay.
And if you have a chaotic system, any noisy observation means essentially then, even if you have full observations,
yeah,
but noisy, then the prediction if you just use the observation at a given time,
Yeah.
the errors will grow exponentially fast for a chaotic system.
But if I just, I don't have to, suppose I want some weather or something, I don't have to predict the weather for next day, let's say like what happened in 1 hour.
Yeah.
So for that probably I can, even the nonlinear equation, I can just get it. And then from the next one, I can just...
If you already use the information that you already have, which is what filtering theory essentially does, then it improves upon it.
Okay.
So a conditional distribution certainly is better than just using the observations. And on top of it, the observations are never complete.
Okay.
So we don't, I mean, we are far, so there is at least a couple of orders of magnitude difference in the number of states variables that you want to estimate and the number of observations available, which is, it's about 10 to 6 or so, or 10 to 8 is the number of state variables you want to estimate in the real weather prediction problem. And the number of observations is about 10 to 3, 4, 5, depending on.
So the other one you just draw from some distribution then, is it? Or
But no, if you just randomly do this, it's not a good idea. That's why the filtering theory,
okay. So
the
that
systematic way of propagating the
other
information forward in time.
Okay.
Okay. Thank you, Amit, again for the talk. And this talk ends this session.